Hello, welcome to Organic Chemistry Companion. Today we'll be going over the mechanism of the Wittig reaction. So the Wittig reaction is a reaction between a carbonyl compound like an aldehyde or a ketone. I'm showing an aldehyde in this case with a phosphorus yelid that looks like this. And I'll talk a little bit more about what that is and where it comes from. The product of the reaction is a new molecule with a carbon-carbon double bond, so it's really useful for building carbon-based scaffolds and bringing together carbon-based fragments. So first of all, let's talk about the phosphorus yelid. So if you've never seen this before, this essentially is the coupling partner for the carbonyl compound in this reaction. In some cases, you'll need to make these from scratch, and so I'll just very briefly talk about where these come from. So this phosphorus yelid typically comes from triphenylphosphine and an alkyl halide. Let's use ethyl bromide in this case. So phosphorus has a lone pair. It's going to attack this carbon, which is an electrophile. And then bromine is going to be eliminated. And the product of this reaction looks like this. Now, phosphorus has a positive charge. And then you also have the bromine as the counter ion. So this is a phosphonium bromide salt. And this is a precursor to a yelid. And what you need to do to generate the yelid in this case is add a base. So typically you'll see either sodium hydride or T-butoxide. I'll just use base or B as a generic base. It's going to deprotonate next to the phosphorus. And then that will give you this species. So this is a phosphorus yelid. It's a resonance form of what I've drawn here. So both structures are correct. I actually prefer this structure sometimes because it kind of teaches you how the phosphorus reacts in this reaction. So I'm going to erase this, but let's keep in mind that this is the structure that we're starting with, and this is how you make it. Okay, so with every organic chemistry reaction, the first thing you always want to do, of course, is look for the nucleophile and the electrophile. In this case, we're using an aldehyde as our coupling partner, and we know aldehydes are electrophilic at carbon, so I'll just put an E there showing that. It can be nucleophilic or basic typically at oxygen, but you almost always see it reacting as an electrophile at the carbon. The phosphorus yelid, remember the resonance form has a negative charge on carbon. That's actually going to be a nucleophile, and so when we draw the first arrow here, it typically we want to go from the nucleophile to the electrophile, although this is kind of a special reaction because what we're actually going to do is form a ring in the first reaction. So we're going to start our arrow here with these electrons, attack the electrophilic carbon of the aldehyde, and then typically what we would do is move these electrons up to the carbonyl oxygen. In this case, there's a concerted ring-forming reaction, and so these electrons are going to attack phosphorus. Remember, in the resonance form, phosphorus had a positive charge, and so this will give phosphorus a neutral charge now. So the product of this is this. Okay, so we formed our four-membered intermediate here, and to get to the product, you can see all we need to do is form the carbon-carbon double bond. We've formed the single bond that's present in the product. Now we need to make this a double bond, and so the way that this intermediate is going to collapse, we could draw this in a few different ways, but if we start here and move these electrons into this bond, that's going to break this bond. And these electrons are going to go up here. And the reason why this is very good is because phosphorus loves oxygen, and in any mechanism that you draw with a phosphorus reagent, you always want it to form a phosphorus-oxygen double bond. That double bond is very, very stable, and the formation of that double bond is a huge driving force for this reaction to proceed. So this intermediate is going to collapse like that, and that is actually going to give you your product, and the byproduct, just for completeness, is triphenylphosphine oxide. So it's a typical byproduct of a phosphorus reagent like this. So that's how you know you did it right, if that's your product at the end. And so just to talk about a few specifics of the Wittig reaction. So This would be considered an unstabilized yelid because there's no ester or other carbonyl group or anything like that next door to stabilize that negative charge. And so an unstabilized yelid like this gives you the Z alkene. So remember, Z alkenes, the substituents are on the same side of the double bond. You can do a modification of this reaction called the Schlosser modification, and that gives you the E alkene, so the opposite stereochemistry at the double bond. And there's another, perhaps more well-known alternative to this reaction called the Horner-Wadsworth-Emmons reaction, where you use a stabilized phosphorus yelid. I'll do a video on that to cover the mechanism of that also. But that gives you the E alkene. So that's pretty much it for the Wittig reaction. So if you found this video helpful, make sure to give it a like and subscribe for more organic chemistry tutorials. Leave a comment below if there's a concept or mechanism that you'd like to see me cover. If you want personalized one-on-one help with organic chemistry, send a message to my email in the description to book a tutoring session. Thanks for watching. I'll see you in the next video.